Welcome back. Today's lecture is about unsupervised learning. So let's recall what we meant by supervised learning and contrast it with unsupervised learning. So supervised learning, the word supervised, remember, refers to the fact that there's a target, a label that we're trying to predict from training data. So we have features and we're trying to predict the label, and the label supervises the learning. For example, like if you're in kindergarten, you can think of a kindergarten teacher who shows a child in the class a bunch of examples of, say, Johnny, here's 5 examples of a house in Lego blocks. Here's 5 examples of a car, right? And he tells Johnny that these are houses and these are cars. So he's supervising the learning, and the child then looks at it and figures out which features of the house make a characteristic of a house and which features of the car make a characteristic of a car. So that's supervised learning. In contrast, unsupervised learning, there's no labels. So the kindergarten teacher would just show Johnny, here's 10 things. And it doesn't tell Johnny that these 5 are cars and these 5 are houses. And the child then looks at the objects and tries to figure out some patterns. He says, he may realize, these 5 look similar. I don't know what they're called, but they look similar, so maybe I should group them together. These other 5 look similar to each other, and I'll put them in the group. Yes?
So this means we have with supervised we have a Y, and with unsupervised we don't.
Exactly, right. So in both we have features, but as Trevor said, in supervised we have a Y we're given in the training data, that's the true label. In unsupervised learning, it's harder in a sense because we don't have the actual labels. So let's move to slide 1. Most of the course, as we've seen, focuses on the first exercise, supervised learning, where we have labels. But today we're going to talk about the setting where we don't have labels, unsupervised learning. All we observe are the features, which, as before, we'll call x1 through xp. And we want to know how the features relate to each other. So, in particular, what are the goals of unsupervised learning? Well, then, first of all, they're not as clear as they are for supervised learning, where the object is to predict y from x. Now we don't have a y, so the objective is a little more fuzzy. For example, we might want to discover subgroups among the observations. Like in my kindergarten example, right? The child may try to discover subgroups among the objects he's seen. We might want to know, is there a good way to view the data, to find the important features, or the features that have the most variation over the different objects. So we're going to discuss, there are lots of methods for unsupervised learning, but in this short lecture, we're just going to talk about 2 of the most important ones. First is principal components analysis, which is a tool for viewing data or for pre-processing the features for use later in supervised learning. And the second is clustering, which is a group of methods class of methods for grouping the objects into different subgroups. Okay, so we'll talk about those 2 methods today. But let's say a little more in general about the challenge of unsupervised learning. As I mentioned, it's a little more fuzzy because there's no simple objective like prediction, right? There's no y available, so we're not predicting. The objective, as we saw in the previous slides, is a little more fuzzy. But nonetheless, unsupervised learning is actually of growing importance, and there's a number of reasons for that. Well, first of all, let's see some examples. Examples actually we'll see at the end of the lecture. An actual example is we have breast cancer patients from whom we've measured gene expression using gene chips, and we want to group those patients into subgroups of breast cancer. It turns out these subgroups are actually quite different in terms of their characteristics biologically and their survival as patients. Another example, which is in marketing, is to find if we have shoppers, and we can record their browsing and purchase histories. We can group or segment the shoppers into different groups, and then maybe they'll be targeted with different kinds of advertising because their behaviors are different. Another example, which is quite popular, is to group movies by the ratings assigned by movie viewers, like a thriller, romance, etc. Okay. And the other thing that makes unsupervised learning more and more important is that there's a lot more unlabeled data available, and that's because in order to get labels for data, it can be costly or time-consuming. Right? For example,
there's tons of images on the web.
Right.
I mean, everybody's loading up images in Google and other places, and mostly they're unlabeled. You don't know no one's told us exactly what's in the picture, but we have the pictures.
Right, and the point is that that kind of information can be collected by a machine, the features, the images, but the actual labeling, it often requires human intervention, right? And that's going to be more costly and time-consuming. An example of that is our movie reviews on the web, right? A lot of people, they try to predict, they try to correlate movie reviews with movie quality and group movies. One problem there is that if you have a movie review written by a human being, right, it's hard to tell by machine whether or not that is actually favorable or not, right? If the movie review could have some sarcasm in it, right? And for a human reading the paragraph, it's pretty easy to say, oh, that person doesn't like the movie or does like the movie. But for a computer, it's not so easy. So that's an example where finding the actual label can be quite difficult and time-consuming. Okay, so let's start with the first main method for unsupervised learning, principal components analysis. And this goes back probably to the 1930s in statistics, when it was first invented. So PCA produces a low-dimensional representation of a data set, and it finds a sequence of linear combinations of the variables or features that have maximal variance. And at the same time, they're uncorrelated. So we're going to see there's a first principal component, which has the highest variance across the data. It's a linear combination of the features. And then a second component, which is uncorrelated with the first, which has the highest variance under that constraint, etc.
Just imagine you have tons of variables, and many of them are correlated. That can be quite an unmanageable set. What principal components tries to do is pare the set down into some important variables that summarize all the information in the data, and that's these principal components.
Right, and that can be very useful just as a way of viewing the data. If you have a high-dimensional data set, you just want to have a look at, gee, what's really happening here, what's important. The principal component view is one of the most important ways of displaying the data. And second of all, if you have a lot of features that you want to use for supervised learning, the principal component summary of those variables can be a good way to use, a good set of new variables to use for supervised learning.
Principal components and the techniques related to it is one of the most widely used tools in statistics and data analysis.
Okay, so let's actually define principal components. So we have a set of variables, x1 through xp, and the principal component, first principal component, z1, is a linear combination of those variables. And it's a linear combination defined to have highest variance across the data set. Now, of course, we're going to choose weights. Well, it's defined by a set of weights, phi1 through phi p, but if I was allowed to make those weights as big as I wanted, I could make the variance of z1 as big as I wanted. So we need some constraint on the phis. And the natural constraint is that they're normalized, so the sum of their squares is 1. Okay? That now makes the problem a sensible one to choose a set of weights that has the highest variance. Those weights are called loadings in some areas of statistics and other social sciences. So the phi11 through phi1p are the loadings of the first principal component, and the principal component, the loading vector, is the set of those p numbers.
If you didn't constrain them, of course, you could just make them much bigger, and that would just make the variance higher. So you need to tie them down.
Exactly. So here's an example. Before we talk about how to actually compute the components, let's just see what the result of the first two components for this data, which is ad spending versus population. So here's the red points are the data points. I plotted them against these two variables. So p is just 2 in this example. The first principal component is given by the projection of the data onto this line. So this direction has the highest variance among all combinations of the features in this data. Correspondingly, this has the lowest variance, right? Yeah, that's true. This has the lowest variance. So here's only two components. So I've got the highest variance, the first principal component. The second component is also, well, it's got the highest variance with the constraint to be uncorrelated with the first component, which means it has to have right angles with the first component. And there it is.
If you only have two variables, you can only get out two components.
Exactly.
But just for illustration, we show you two variables.
Okay, so how do we actually compute the components? Well, now suppose we have our data, which are features n by p, the X matrix. And now, since we're only interested in the variance, we can center the variables to have mean 0, right? We don't care about the mean, we're just worried about the variance. So in other words, in particular, specifically, we make the column means of x0. And then we want to find the combination of the variables that has the highest variance. Remember, highest variance under the constraint that these loadings have sum of squares 1. Now, since the data have been arranged to have mean 0 in the first step, that means the z's have mean 0, and hence the variance is just the sum of the square of the z's is the sum of their squares. Okay, so to continue the computation, we have the z's, which we've defined to be the sum of the loadings times the features. And so now the problem now we can replace the z's by their expression from the previous slide, and we want to find the highest variance now, which is this expression, subject to the fact that the loadings have to be normalized, right? So this is now just a computational problem where the unknowns are these phe's, and the optimization can be done by the singular value decomposition, which is a standard technique in numerical analysis, which we won't cover, but if you want to read about it yourself, it's very interesting and very important in a lot of areas of statistics.
And it's covered, for example, in our book, Elements of Statistical Learning.
So when we've solved this problem and we got the best loadings, the resulting z values are the first principal component, which we'll write as z11 to zn1. Okay.
So it's like we've created a new variable now. We had our original p variables. Now we've created a new variable, which is the c1, which has n values just like each of our original variables.
Exactly. So now we can think of that geometrically, and we'll go back to the picture in a moment. So the loading vector is a direction on which a direction of the features that if we project down that direction, has the highest variance. And the values of the projected data are the principal component scores. So let's go back to the picture of the two-dimensional one. Okay. So I said this was the first principal component. That means the loading vector is the vector that points in the direction from the middle to the northeast, right? So here it might be something like maybe 1, 1, or roughly, okay? So that's the combination of the features that we compute using principal components. The actual computed values are the projections onto this line. So we could start, say the origin could be here. We could just measure each point. We take its projection onto this line. We measure how far is it away from, say, the origin here. Okay? So the z's for these guys would be positive, and the z's for these guys would be negative. So we replaced each point by basically how far along this line is it. And that's the first principal component.